This is the last lesson of calculus. It's units 8.9 through 12 combined. Volumes of revolutions using the washer method. So here's a graphical representation that I found online on Desmos. And so before we've used triangles and rectangles to make another axis to find the height of the 3D shape. In this method, we are going to be revolving around the y-axis. So if you can picture that solid, and if I revolve it around the y-axis, notice how it kind of makes a 3D shape like a cup, with the insides being V-shaped and the outsides being curved. Now, a couple important things to note is that there are two circles down here. There's like the outermost circle, that's going to be important, and the innermost circle. The outermost circle has a radius, we call it capital R, and the inside circle is lowercase r. And again, you can revolve these around more than just the y-axis. You can rotate them around the x-axis like this. And look what happens here. It looks like it's kind of like an open bowl. Right, again, you still are going to have your two circles. You're going to have your big circle that goes to the edges and your inner circle. So again, this is going to be the same thing. There is a formula with this. It's pretty simple. A couple things to note is that you're going to be revolving around a line. And again, depending on if it's vertical or horizontal, depends on if you use dx or dy. So if you revolve it around an axis, a horizontal axis, you're using dx. If you revolve it around a vertical axis, you're using dy. And just know that the line of revolution will never pass through the object. And here is the formula right here. It's pi times the integral with the boundaries of integrations, and then it's your big radius, subtract your little radius, dx. And your boundaries of integrations are from a to b. Okay, so let's do example 1. Now, this is from the previous section, example 1, and then part B is from the new section. I'm sorry, I meant A is from the previous section. So here you go. Your boundaries are defined by two functions, and you want to find that area A. In my original paper, I wrote it R, but it's better to write A because we're going to be using R as a radius. And so if I want to find the area between two curves, I just take my topmost equation, which is square root of x, and then subtract it from the bottommost equation, which we represented with e to the negative 3x. So we have our integral from a to b. We'll find a and b in a second. Now our topmost equation is square root of x. Subtract our bottommost equation, which in this case is e to the negative 3x dx. And you'll just type this into your calculator. You do need to find a and b. So a in this case is down here. And then to find it, you need to solve the square root of x equals e to the negative 3x in your calculator. And again, you'll do that by making them each a graph and finding where their intersection is. If you do this, you're going to get x is approximately equal to 0.238 7. And we know our b, that's this boundary, that is x equals 1. And so, yeah, we have dx, we have all of our x's, and these are boundaries of x. And so if I type this into my calculator, I'm going to get that the that the area is 0.4426 units squared. Okay, now we're going to find the volume of revolution. It's going to be pi times our boundaries from A to B. And just to note, this A and B are the same as this A and B up here. We're going to have our capital R squared minus our lowercase r squared dx. And so if we go back up here to our picture, if we are rotating around the axes, this figure is going to kind of do something like this. Because again, this gets rotated around and this gets rotated around. And if we come up here, this equation to the line is your little r. Let's do it in a different color. Let's do it in green. And then basically from here to here is your big R. And so we just need to write the equation of this R and this R. Now, if you recall, if I want to know the size of a line, you just take 8 minus 2 to show that the height here is 6. And we're going to do the same thing. To find this R, it's this point minus this point. Now this is defined by 1, and this point is defined by this equation, which is the square root of x. So little r is going to be 1 minus square root of x. Big R is going to be 1 minus e to the negative 3x. And that's it. We just put those in our equations and plug them into the calculator. Again, this was our big R squared minus our little r squared. And our boundaries are the same as above from here. So it's 0.2387 and b is equal to 1. And you just type that into your calculator and you're going to get that the volume of that shape is 1.4235 units cubed. And there you go. There's example 1. Oh, and I guess I forgot to mention this, where this comes from is when you're doing the big radius, notice that this is a circle, right, with radius r. And so the formula is really pi r squared. But the r is the difference in r's. And then the pi is right there, and then the square, well, obviously goes with the square. So it's defined by, or it's derived from a radius of a circle. So now our last example. And so whenever you see, look, what's the volume of the solid generated over the line y equals -1? So we are going to revolve around that line. So we are using dx. And so we just need to, again, do the same thing. Find the large radius, find the small radius, and then find our boundaries of integration. So in this function, since we're going to be revolving around this way, our little radius, we'll do it in green, is going to be from the function g of x, which is in this case is this function, minus -1. So r is going to be g of x minus -1. Again, the -1 comes from here, and this is g of x. So the g of x is 4 to the negative x, and then this minus -1 turns into +1. And then my big R, which I'll do in blue, and I'm sorry I can't draw a straight line, is going to be this top function, which is f of x, minus the bottom function, which is -1. Now my big R is defined by 1/4 sine of pi x, and minus -1 turns into +1. So let's fill in what we have. And there's our equation. We just need to find a and b. So to find a and b, we need to solve the two functions together. So we'll do this in our calculator. You set those each as their own unique graph, and then find where they intersect. And if you do this, you're going to get a is equal to 0.1782, and b is equal to 1. So fill that in. And there you go. Type that into your calculator, hit equals, and you should get a volume of 4.5587 units cubed. And there you go. That is the last lesson.